Hi, my name is Michelle Perry, and I'm going to give you a brief introduction on my research in nuclear structure and gamma-ray spectroscopy. In 1948, Maria Gobert-Mayer realized that nuclei exhibit shell structure similar to the atomic orbitals, and with a strong spin-order coupling term added to the textbook example of a harmonic oscillator, the magic numbers seen in nuclei are reproduced. Now this model holds for stable nuclei, which are represented on the plot on the right by the black boxes. Above these stable nuclei are proton-rich nuclei, which have an excess of protons, and below the stable nuclei are the neutron-rich nuclei, which have an excess of neutrons. These regions are very interesting now because their nuclear structure is not well known. We see shifts in the shell structure, which are producing different magic numbers. In order to study the nuclear structure in these regions, we use gamma-ray spectroscopy. When nuclei are excited, nucleons jump up in the shells and produce excited states. These when a nucleus is in an excited state, it then decays back to the ground state via gamma emission. We detect these gamma rays and can extract nuclear information about the states, and thus about the nucleus. In order to produce excited nuclei, we accelerate nuclei at the FSU John D. Fox Accelerator Laboratory. The FN tandem accelerates our nuclei. We have a positively charged central contact where negatively charged ions are attracted to. Upon passing through the central contact, the negatively charged ions are stripped of their electrons and become positively charged, where they are then repelled away from the positively charged central contact. So it's a two-stage accelerator. We then detect the gamma rays with our high-purity germanium gamma detectors, which are also Compton suppressed. For particle identification, we have silicon particle telescopes, and this can separate out the nuclei that are produced in the reaction. In the figure on your left, you have the protons, deuterons, tritons, and alpha particles that are emitted from a compound nucleus in your reaction. By selecting a certain channel of these nuclei, you produce a gamma spectrum, which is shown on the right, which you can then analyze to get your nuclear structure data. The figure on the left shows an example of coincidence measurements that were taken at Florida State University. By looking at coincidences, you can build up a level scheme that is shown on the right, and you can also, with these gamma rays, extract spin and lifetime information for these states as well. Once you have built up a level scheme, you compare your results with shell model theory, and you also compare it with surrounding isotopes. And from your results, you can extract more information about the nuclear structure in the region you are studying. Some interesting research that's being done at Florida State right now is studying the island of inversion, where the ground state configuration of these nuclei exhibit unusual behavior. And this is done by Vandana Tripathi and Stephen Paget. We also have a rare carbon-14 beam that is used to probe little explored regions in the neutron-rich mass 20 to 30 region and build up level schemes and determine nuclear structure information here. And Tricia Hinner, Sanjan Lee, and Michelle Perry work on this. Another interesting topic is studying nuclei at the limits. And this is studying neutron-rich nuclei along the neutron drip line. And Caleb Hoffman has studied the unbound neutron-rich oxygen-25 isotope. And that's all.